Okay, let's dive in. We are in section 400, and we start today from dot 11. All systems are continually importing as well as exporting energy. Physics has found only myriad pattern integrities of comprehensively non-simultaneous and only partially overlapping evolution. Let's tackle the first half of the sentence. So physics has found only myriad pattern integrities. Pattern integrity is a well-defined term of Buckminster Fuller's, and it means that something has structure so that it coheres long enough for us to sense it and be aware of it. Comprehensively is a key word as well. Com, together, prehensile, also relating to holding physically or holding mentally. Comprehensively, non-simultaneous and only partially overlapping. Again, a very core concept that the universe doesn't occur all at once, and it's backed up by Einstein's space-time, in that things that are distance apart are not existing at the same time. We see the stars, even though they're many light years away. We're actually seeing what they sent to us many light years ago. Of disintegrative heres and reintegrative theirs. Here, the dichotomy of disintegration, which is radiation, and integration, which is gravity. This dichotomy is very important to Fuller's work, which are omnilocal, everywhere local, vary intertransformabilities. They're varying, and they are that means they relate to themselves, transforming, of limited duration identities of an apparently eternal physical universe, regenerating mathematically treatable energy quanta. Comprehensibility of systems. As we indicated, comprehension is comprehension, how we can hold it together as a whole in our mentality as well as in our hands. All systems are subject to comprehension, and their mathematical integrity of topological characteristics and trigonometric interfunctioning can be coped with by systematic logic. So here, very important to Fuller, and in a minute we're going to hear about another systems theorist down below, Bertalanffy. Fuller differs from Bertalanffy in that he thinks of systems as geometries, topological and trigonometric, relying on triangular coordination, because triangles are the only physical form, the minimal physical form that has structure. Section 21. A system is the antithesis of a non-system. A non-system lacks omnidirectional definition. Non-systems such as theoretical planes or straight lines cannot be found experimentally. We are scientifically bound to experientially discovered and experimentally demonstrable systems thinking. So here, Fuller is taking a stab at a theme he will return to constantly, which many people find confusing, is that Euler's planes and straight line mathematics actually has limitations, and he criticizes it. This can be surprising to many people because, after all, it's the foundation of today's mathematics. It's what you learn in school, and it's what enables machines to coordinate. It's the basics of our metric system. It's the basics of the moon launch, for example, which we're going to talk about in another 2 paragraphs. But Fuller has a critique of that, which will be found across the entire book. And part of that criticism is that an infinite plane cannot be considered a system by definition in Fuller's thinking, and I think in Bertalanffy's thinking, systems are by definition finite. They close in on themselves, and Fuller's reminding us they might not do that all at the same time. They partially overlap, as we set up here, but they are finite and they close in on themselves. 3 more to go today. Section 22. General systems theory treats with phenomena that are holistically comprehensible. The objects of our experience are finite systems. On to 22. General systems theory treats with phenomena that are holistically comprehensible. The objects of our experience are finite systems. Their superficial outlines close back upon themselves multidirectionally as a systematic continuity of relevantly contiguous events. Section 23. Maximum system complexity consists of a dissimilarly quantified inventory of unique and non-intersubstitutable components. That is, Euler's irreducible system aspects of vertexes, areas, and edges exhibit the respective dissimilar quantities 4, 4, and 6 in the minimum prime system, the tetrahedron. This demonstrates the inherent synergy of all systems, since their minimum overall inventory of inherent characteristics is unpredicted and unpredictable by any of the parts taken separately. Systems are unpredicted by oneness, twoness, or threeness. This explains how it happens that general systems theory is a new branch of science. Okay, there's a lot going on in this paragraph. Just to break it out a little bit, at first, we have this sentence where the maximum complexity consists of dissimilarly quantified inventory of unique and non-intersubstitutable components. In other words, there's a diversity required to constitute a system, and Fuller's beginning point is always the tetrahedron, and so he points out here the diversity in a concept like the tetrahedron, which is that it has things that Euler called vertexes, Euler constituted as areas, and edges. And that is, of course, how it's taught today in conventional schooling. And here in this book, Synergetics, we're going to think of these things in different ways, in conforming with how we want to think of systems and finiteness at all times. Then the second half, I believe Fuller wants to say here that these things occur due to synergy. In other words, vertices themselves cannot create a system. Areas themselves would not create a system, and edges themselves. It's the coming together of these non-intersubstitutable components, their cooperation, that makes a system. And finally, he points out that 1, 2, or 3 is not sufficient. Again, another theme of Fuller's, the tetrahedron has a certain fourness. It has 4 windows, 4 vertices. And our final paragraph for today, a little dip into history. Paragraph 24. General systems theory is another example of evolution by inadvertence, a favorite theme of Fuller's, that evolution happens maybe not by planning, but by life finding what it needs to go forward. It developed fortuitously to accommodate the unprecedented and vastly complex undertakings of the late 20th century, such as the 10 million separate and only partially overlapping critical path tasks that had to be accomplished and tested to foolproof reliability en route to countdown to eventual blastoff, moon landing, and safe return to Earth, which found all conventional mathematical theory wanting. Fuller here, of course, in his lifetime, he lived to witness the moon landing when the United States NASA undertook within 10 years to land a man on the moon, and it revolutionized what we today call project management, and it used critical path theory. They broke it down into steps, like getting off the planet was one challenge, then getting to the moon was another challenge, then landing on the moon was a third one, then getting back up, fourth one, and then traveling back to Earth, which is kind of similar to traveling to the moon, but then landing on Earth. There's the safe return to Earth over here. So this was really a massively complex and interconnected systems, and Bertalanffy's, as we're going to see in a moment, had codified an idea of general systems theory, and that did help inspire the Apollo program's operation. back to the paragraph. It required the development of the computer and star-focused instruments and computer programming arts, together with operational research, which guess improvises the inventory of parameter of variables that must be progressively programmed into the system in order further to reduce the magnitude of tolerated errors consequent to trial bird, rocket vehicle flight, trajectory control, as the vehicles are progressively zeroed in to progressive target rendezvous with celestials and entities. Neither differential and integral calculus, nor probability statistics, nor any branch of specialized hard science had accredited synergy as an a priori assumption. General systems theory, which recognizes synergy as inherent, was discovered and named by the biologically inspired Ludwig von Bertalanffy. And next time we read, we'll hear more about this. Bertalanffy's general systems theory gave language for thinking about wholes, interdependence, and feedback loops. And we hope you'll come back and read the next section with us tomorrow.